Good evening and welcome to Season 1, Episode 1 of the Late Night Conference. My name is Wilhelm Huck and I'm your host tonight. I'm super excited that we finally get started, a little bit nervous too, but what we really try and achieve in the next 6 months or so is to bring some cutting edge science to a much broader public, especially the bachelor and master students in natural sciences here in Nijmegen, but anywhere in the Netherlands or indeed anywhere in the world can join us for some really exciting science. Not only exciting and amazing science, but you also get the chance to actually get to know the people behind the science, to learn a bit more about their motivation, to see what kind of career changes they made, or indeed what happened after they won the Nobel Prize. And it is you have the opportunity to ask questions in the chat about their science or about their career choices, and maybe you can get some advice from the guests that we have on our show. Now, Season 1, we want to explore the origins of life. Are we alone in the universe? Where do we come from? These are questions that have been posed by mankind for millennia. And what we have done is we have invited a series of experts in the field, world-leading experts, who are going to discuss with you topics such as the formation of planets, the development of prebiotic chemistry, chemistry in between the stars, or the earliest signs of life on the young Earth. And it's my great pleasure to introduce you today to Professor Ewine van Dishoeck of Leiden University. She is a professor of molecular astrophysics and the president of the International Astronomical Union, a winner of the Spinoza Prize and the Kavli Prize for Astrophysics. She studied chemistry and mathematics in Leiden University, and she also obtained her PhD there before going to Harvard as a junior fellow. After that, she took up a faculty position at the University of Caltech, and then rejoined Leiden University as a professor of molecular astrophysics in the early 90s. As I said, she has been extremely successful in her research, and what she is doing is really to use the universe as her laboratory and studying that laboratory with the world's most powerful telescopes. And you would say, what is going on in that cold, vast, empty space between the stars? Well, you'll be surprised to hear that there is a lot of chemistry going on. Over millions and millions of years, molecules with an uncanny resemblance to our building blocks of life are being formed. And today, Professor van Dishoeck is going to give you a glimpse of a totally different world. So we are looking forward to her talk. Professor van Dishoeck, the Zoom is yours.
Thank you very much, Willem. It's a real pleasure for me to be here with you virtually tonight. I wish we were in a real cafe. I really always like the excitement of being there, the little bit of roezemoes that is going on there. But we will have to do with the Zoom. And I think the wonderful way, actually, of Zoom is that it's not just, a few tens of people that can participate, but it is actually many more people that can now connect. And that's what we've seen over the past 9 months, that even though we are far away, sort of on a personal basis, yet we seem to be more connected than ever. Now, what you see here is actually a picture of people looking back at our own Earth, the pale blue dot, as we call it, showing basically the fragility also of our little Earth. And I'll come back to this because this was a celebration that we had just prior to the pandemic when it started to hit. So keep that image in mind. As Willem already said, our origins, that's a topic that fascinates not only scientists, not only astronomers, not only physicists, it's really something that fascinates mankind. And you see that, throughout society. You can see it in exhibitions, you can see it in poems, you can see it in music, But one of my favorite ways of looking at it is through paintings. And of course, in the Netherlands, you don't have to go very far. You just go to Van Gogh and you see some of his beautiful starry nights. And you read the letters of Van Gogh, and he says basically, I had to paint this the night. You know, he's so fascinated by it. But you can also go to the completely other side of the world. This is a painting from the Aboriginals in Australia, who of course have this beautiful southern sky above them. And what you see here is a dreaming. So that's basically an integral part of their society, the dreamings that they have. And this is the so-called Milky Way dreaming. So here you see the spiral arms in the Milky Way, and you see here the seven sisters, zeven sterren, de Pleiade, in Dutch, Pleiades, here actually put into the heart of the Milky Way, because this old man Orion is actually chasing them. But all of these stories have in common that they ask the questions, you know, where do we actually come from? And are we alone? And what I'm going to show you is that through a number of observations, and especially new techniques, technology plays a very important role in this, that we are getting a step closer to answering that question. So what you see here is actually the Milky Way. Here above beautiful scenery, you see here the Magellanic Clouds, but here you see the Milky Way, the dust clouds in the Milky Way. And our origins are actually in one of those dust clouds. That's where we come from. Now, if we would sort of be able to step outside our Earth, outside our galaxy, and basically look down on our galaxy, then it would look something like this. So this is obviously an artist's rendition, but it is based on real astronomical data. So here's our Earth, here's the sun, here's our sun. Our sun is, of course, only one of a few hundred billion of stars here in our Milky Way. Here you see the various spiral arms again. Here in the center, that's where the black hole is. That's where the Nobel Prize for Physics went to this year. And then you see actually surrounding that, basically on a scale of some 50,000 light years, you see basically the various stars in our galaxy. So what we see is that we live on a small rocky planet around a quite ordinary star, somewhere in the outskirts of our galaxy, our Milky Way. And of course, our galaxy, our Milky Way, is only one of several hundred billions of galaxies in the universe. So that puts immediately this whole question as to, are we alone, into a quite different perspective. Now, one of the most exciting developments in astronomy over the last 25 years has been the discovery of exoplanets. An exoplanet, that's a planet around another star than our own sun. And the first discovery was in 1995. They were, of course, speculated already for centuries. The old Greeks were already writing about them, but the real scientific evidence did not come until 1995. And that was also awarded the Nobel Prize in 2019. Since then, there have been many observations, both from the ground and from satellites in space, especially this satellite, the Kepler satellite, that was able to look at the tiny little dips in the intensity of a star when a planet passes in front of it, just like Venus passed in front of our own sun a number of years ago, and you also was a tiny little dip in the intensity of the sun. Through that transit method, as it's called, we now have quite some detailed information on the statistics of exoplanets. And we know that now, on average, every star has at least one planet. But the bulk of them are actually not similar to those in our own solar system. Of course, in our own solar system, we have large planets like Jupiter, like Saturn. We have small planets like Earth, but the bulk of them seem to be somewhere in between Earth and Neptune. Neptune is about 10 times the mass of Earth. So we call them super Earths or mini Neptunes. Those seem to be the most common type of planets, at least in our galaxy. And they are of a kind that we don't have in our own solar system. So that's already interesting in itself. Directly related to this whole question is actually how were we formed some 4.5 billion years ago? Literally $1 billion question, because in order to answer that, you need to have space missions in order to study the material in the outer solar system. So you see here, for example, a comet. A comet is, of course, a mix of ice and rock. And they have been preserved for 4.5 billion years in the outer part of our solar system, and not much has happened to that material. So they have the most primitive material, actually. Then in the inner solar system, you have the asteroids, and very excitingly, we have had missions like Hayabusa 2 and OSIRIS-REx that have just gone to an asteroid. They've collected material. The Japanese mission has already come back to Earth, landed in Australia. The other one is on its way back to Earth, and they provide the material that you can actually study in a laboratory on Earth. So the Rosetta mission actually in 2014 landed on a comet and studied the material there. These missions actually bring back some material to Earth. And together they tell us the story as to how we were formed some 4.5 billion years ago. So let's start actually our story. Where are these planets formed? Well, for that you actually have to go to the space between the stars. I mean, you've all looked up to the beautiful night sky, and you've seen all these stars. You may have seen a planet, maybe once in a while a galaxy, but few of you may have realized and asked the question, what is actually in between the stars? Well, that space in between the stars is not empty, but is actually filled with a very, very, very dilute gas. On average, there's only 1 atom per cubic centimeter. Whereas here in your room where you're sitting, there are 3 times 10 to the 19 particles per cubic centimeter. And even in a good ultra high vacuum in a laboratory on Earth, like the laboratories there in Nijmegen, and they still have of the order of, say, 100 million particles per cubic centimeter. So it's really very empty there in space. And that is what makes it so interesting also for a chemist like me originally to study this, because we can study actually chemistry and physics under very unusual conditions. Now, one of the top interesting regions here is here in the Sword of Orion. This is the Orion Nebula that you see here beautifully imaged by the Hubble Space Telescope. Now, these clouds, actually, these dark clouds, these are some of the largest structures that we have in our galaxies. They can be several light years across. They are also the most massive and the most cold regions. And they are just a little bit above 0 in temperature, about 10 to 20 degrees on the Kelvin scale. And they are so dark because they contain these tiny little dust particles, about 1/10 of a micrometer in size. So if you take my hair here, then if you look at that, that is about 1 millimeter in diameter. So this is about still more than a factor of 1,000 smaller. So think of them as small dust grains, like sand on the beach, but then a factor of 1,000 smaller. And so they absorb and scatter the light, and that's why these clouds look so dark. But if I would now point some of my telescopes here at this region over here, this is where I would see new stars actually being formed at this moment, and also lots of molecules. So how is actually a new planetary system formed? Well, here we have one of these dark clouds. And for a long time, say 10 million years, such a cloud can be stable. But then in the end, gravity basically takes over, and it will start to collapse under its own weight. And because the cloud always has initially a tiny little bit of rotation, you tend to form a disk around the young star that you see over here. Now, on much smaller scales, this is the scale actually of our own solar system. We're using the units of astronomical units, which is the distance between the sun and the Earth. Now, in these disks, they are very important because this is where the planets can form. And we know that actually from our own solar system, the so-called solar nebula hypothesis, because it was realized already by Kant in 1755 that, yes, all the planets are in one plane. And so the most logical explanation is that they were formed and they all rotate in the same direction. So the most logical explanation is that they formed out of a rotating disk of gas and dust. And so that's what you see here, and you see also how a young planet here in this disk actually can sort of sweep out and carve a gap in that disk. Now that was an animation. This is real data. And this is the excitement that we have at the moment, is that a new facility, Alma, that I'll come to in a moment, is actually providing us images of these planet-forming disks. This is sort of the scale of the orbit of Neptune. That would be over here. This is a somewhat bigger disk, a young disk, but you see already here some of these depressions here in the emission that we're seeing here from cold dust particles that signify that there may actually be ongoing planet formation. And this is not the only disk. There is actually a whole set of disks that have been imaged now by our and by other groups that show these fascinating structures, caps, spiral arms, cavities, little asymmetric features that are all indicative that there's something going on with these disks and that it's likely planets. We can't see the planets themselves, but we can see the result that they have on that disk. So to summarize this part of my talk, nearly all young stars are surrounded by disks. That's what we now know. The sizes of these disks are comparable to those of our own solar system. The masses of most of those disks are enough to form planets, especially in the early stages. And the structures in these disks actually point to planet formation in action. And so the bottom line conclusion is that most stars are actually born with enough material to form planets, and that planet formation, at least the ingredients, are common. I already mentioned that technology is very important. So let's talk a little bit about it, because we couldn't have made this beautiful image if we didn't have some of the new facilities. So here is our artist impression of one of these disks. And if it was as big as we see over here in this image of this dark cloud from the Hubble Space Telescope, then we would have no problems in seeing it. But it is not that big. It's actually tiny, 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 tiny. Oh, it's so tiny. There it goes. It's just like a little dot here on this image. And that was the challenge. Not only are these disks difficult to see, we cannot see them at optical wavelengths, we cannot see them with the light that our own eyes are actually seeing. We need to go to longer wavelengths. We need to go to the infrared, to the millimeter part of the spectrum. And then they are also very small. So we needed really new facilities and the sharpness of them in order to zoom in on these disks. So here is actually Alma. This is the first worldwide collaboration actually in astronomy, collaboration between Europe, between North America and East Asia to together actually put this array of some 66 radio antennas on a high altitude plane in northern Chile. And so the wavelengths at which these telescope measure is a millimeter wavelengths, say from 0.3 to about 3 millimeter wavelengths. Or if you like to think in gigahertz, then it's about from say 100 gigahertz up to 900 gigahertz. Why did we go there to northern Chile? Well, as the New York Times even figured out, it's truly high and dry there. As you see here is the beautiful volcanoes here on the border of Bolivia and Argentina, this sort of the three-way border that is there. And you see there this little town of San Pedro de Atacama, that's very close to where Alma is located, right over here on this high altitude plateau. Here you see not an Alma transporter, actually this is a real Alma transporter. It's like a big truck that can actually pick up these antennas and drive them up to the high side. What you see over here is actually the technical facility where all of the antennas were assembled and tested, and then once they were tested, they were driven up here on this road in order to be put into the array. So it's really a testimony to the high-tech technology to build, get components from all over the world, bring them to a harbor in northern Chile, then drive them up here to the sites, test them, put them together, put them on this big truck, and then put them here into the array at the high altitudes. Now, all of these telescopes have eyes and ears. The eyes are basically the receivers, and these are very sensitive so-called SIS junction heterodyne receivers. And the Netherlands actually has a lot of technology, has developed a lot of that technology, most notably for the Herschel mission, the HiFi instrument for space research, organization Netherlands Esron Institute, but then that same technology has subsequently been used for Alma. These are incredibly sensitive receivers that work sort of very close to the quantum limit, and we can be proud that the Netherlands has provided several of these receiver bands that you see over here. So here is a picture of Alma when it was being inaugurated in 2013. It has now been operating for a number of years. And it's still, to me, a breathtaking experience to be there at the site. I was there about a year ago, and I've been there already quite a number of times, but every time I am there, it's still breathtaking, both figuratively, but also literally, because we are there at 5,000 meters altitude. So here is actually where you see Alma working, and so this works as an interferometer. That means that the signals of all of these telescopes are connected to each other as if they were one gigantic array with a diameter of 1 kilometer up to 16 kilometers. And in that way, it allows a much sharper view, actually, of these sources. So they can track them on the sky here for hours and hours, and in that way get a very sensitive image of the objects. So this is happening at the moment. We are, of course, also looking to the future. Hopefully this year, the James Webb Space Telescope will be launched. That is sort of the next step after the Hubble Space Telescope. It will have a 6-meter diameter. That's way larger than that of Hubble, only 2 meters. And again, there is Dutch technology on board in the mid-infrared instruments, where the Netherlands has also provided quite an important part of the spectrometer optics. Then in a little bit later is going to be the extremely large telescope. It's already being built in northern Chile by the European Southern Observatory. It will be the largest telescope on Earth, 39 diameter, and the largest optical telescope on Earth, 39 meters diameter. So it will be very sensitive, can look very sharp. First light around 2027. And again, there will be a Dutch instrument in the mid-infrared on board there. And both of these instruments will be very important for characterizing the atmospheres, the composition actually of the exoplanets. And so to really ask the question and search for signs of life in those exoplanet atmospheres. So stay tuned for new excitement that will come there as well. Now, I've been asked to also provide a few words, say a few words about myself. So let me start here. This is what my parents envisioned for me. They had great expectations, obviously in the medical profession, as you can see over here. Crawling towards the university. They clearly had a university career for me in mind. I never had much inclination to go into medical director, but I've always gone more for the natural sciences. But sort of this quote that they gave me that comes from the Aeneas, Vires acquire terrendo, she will gather her strength en route. I think that was very appropriate. You know, it's not that you can do and know how to do things from day one. No, it's really step by step that you learn how to do this and work towards your career. So I really liked chemistry. I started studying chemistry because I had an inspiring high school teacher. I had a pretty bad physics teacher. So this is, again, the importance of good teachers. High school teachers, I can't say that enough. So important. But then when I came to university, I actually, got good physics teachers. And then I discovered that I liked physics just as much. And so chemical physics, quantum chemistry, quantum physics, that seems to be the perfect marriage of these two. However, it turned out that even though I wanted to continue there for my PhD, it turned out actually that the professor had died, has passed away. And so I had to look elsewhere. It was not going to be a succession for quite some time. And it was then actually my then boyfriend and now husband who had just was studying astronomy and mathematics. And he had just had a course on interstellar medium, on interstellar clouds. And he had heard about these interstellar molecules. And he said, well, if you like molecules, why not go for interstellar molecules? Isn't that something for you? And so that is how it basically started. And that's how I gradually moved away from chemistry. I would say I didn't move away. I basically made the transition of applying chemistry to astronomy. So lessons for those of you who are thinking about choices that you have to make. One thing I've noticed that it's always good to make sure that you are good at least one thing so that you get noticed. So it's better to do one thing really good than lots of things average. And then also dare to look elsewhere and make an interdisciplinary jump. So my career in a nutshell then, as Willem already mentioned, from Leiden to Harvard. For postdoc years, also Princeton. We were then in Princeton also for, Tim was in Princeton for 4 years. I was there also for a significant fraction of my time. And then indeed we moved to Caltech, where I got my first faculty job actually in cosmochemistry. There I was actually in the geology and planetary sciences division, yet another sort of interdisciplinary angle. And so the lessons that we learned there is to stretch those postdoc years because they never come back. That's where you can do free research. And also being away from home was so important to build your lifelong network across the world. So that was also very important. And then we came back 6 years, after 6 years in the US, we came back to Holland again. And since that time, I've been privileged to actually work with fantastic young people here. You see here are having our first socially distant group meeting this summer. Good. Then finally, in the final 5 minutes or so, a few words about chemistry between the stars, because I haven't said that much about it yet, but yet it's very important. So this is sort of how an astronomer would look at the periodic table. Mostly hydrogen, a little bit of helium, but that's chemically not so interesting. And then these more chemically interesting elements, carbon, nitrogen, and oxygen, are actually at the level of just a fraction of a promille compared with hydrogen. So this was the reasons why chemists told astronomers, don't even bother to look for molecules in clouds. You won't find them, so empty, so cold. They meet maybe once every 10,000 years, nothing will happen. But fortunately, the astronomers didn't listen to the chemists, and they turned their telescopes to the clouds, and they found one molecule after another. This is a signature here of water. Every molecule, of course, has its own fingerprint thanks to the laws of quantum mechanics, and that's how you can see them. So here you see the rotational transitions of water. But there is not just water, not just simple molecules, but also already quite complex organic molecules. Methanol is actually quite abundant. Ethanol is also quite abundant. This cloud will probably have enough alcohol to fill something like 10 to the 27 bottles of whiskey. And then you have also simple organic molecules like glycoaldehyde that you see here, cyanides, even more bigger molecules like the polycyclic aromatic hydrocarbons that are there. But then also molecules that we haven't found yet. The simplest amino acid, glycine, has not yet been firmly identified. And neither has this little molecule that may not be important for the origin of life, but is definitely important for the maintenance of life. That is actually caffeine. So water has played an important role in my career, especially the Herschel Space Observatory was very important there. This is just one of these signals that we measured in actually a planet-forming disk. From the strength of this signal, we could actually quantify how much water there is and it turned out to be of the order of 6,000 oceans of ice. So clearly quite a bit of water available for making a habitable planet there. We tried to simulate that in our laboratory in Leiden, now under the direction of Harold Linnaerts, where we basically, even though we can't get to such low pressures, we don't want to do that. We don't want to wait 10,000 years for, for a reaction to happen. But we can actually simulate the low temperatures and most of the conditions that you see over here. And through the combined actually observations, modeling, and laboratory experiments, we actually have put together this little simulation as to how we think that water is formed. So most of the water is actually formed on these tiny little dust grains in space. What you see here is once in a day, maybe a hydrogen atom lands on this grain. It can scan a surface, it can find another oxygen molecule. Two oxygens can find themselves making O2. And now we're making actually hydrogen peroxide. Yep, there we go. And now we're making actually 2 water molecules. And these are all steps that have been seen in laboratory experiments. And now we fast forward, we go to say 10,000 years or so, and now we actually are building up sort of this ice layer on this dust grain, this tiny little dust grain. And this is actually how we think that most of the water that we have in our bodies, that we have here on Earth, was actually made some 4.5 billion years ago. And since then, of course, the water has condensed and evaporated and recondensed, but the original bonds between the hydrogen and the oxygen were made already in this very early stage in the cloud out of which our solar system formed. So as one of my colleagues put it, the water on Earth is actually older than the sun itself. Think about that the next time that you drink a little bit of water. All right, so just to summarize this part then, interstellar clouds have a very rich chemical composition in spite of these cold and tenuous conditions. Complex organic molecules in water are formed throughout the forming stars, throughout the entire Milky Way, and there's a large similarity actually in composition with comets. I'll come to that in a moment. The bottom line is building blocks for prebiotic molecules are also widespread. So then we go actually from how do we now actually incorporate this into a planetary system. So we have our tiny little dust grains. They actually grow. They can stick to each other and in that way come into these planet forming zones. So let's look at this little simulation. Yeah, here we have our tiny little dust grains. They can actually collide with each other, and when they collide, they can actually stick. Yep, there they go, they stick, they become larger and larger. Yep, there they go. And in that way, they grow then from small to larger and larger. And so here is actually then the simple story. We start making our chemistry here in this phase when the grains are still very small. Grain surfaces play an important role on that, but then they can coagulate to larger and larger bodies and then eventually become a planet. The comets, the planetesimals, kilometer size, that's a very critical role. That's when gravity starts to take over again. That's sort of the building blocks. And that is why this comparison between what we find in our interstellar clouds and the composition then of these young disks with what we find in comets, like from the Rosetta mission, we find a large similarity, suggesting that indeed a lot of this material from the interstellar medium is incorporated almost unaltered in the forming solar systems. All right, I'll end here, and just one more slide here to show you the broader implication of astronomy. Astronomy brings not just exciting science, black holes, everything that we have big explosions in the universe, but also this whole exoplanets and formation of planets. All very exciting, but it also brings perspective. And one image that really amplifies this sort of importance of the perspective, and that's the pale blue dot. The image that the Voyager mission took 30 years ago When it turned back again, was already past Saturn, it turned back again one more time and looked back at Earth and took this picture. And that's us, the tiny little dot. And that's home, that's what we are. So astronomy and space provide perspective, modesty, and also some tolerance. And so this is where I would like to end with this same beautiful picture and remind us that we're all world citizens under that same beautiful sky. Thank you very much.
Thank you, Ewine. That was a truly fascinating story. Actually, many fascinating stories, both through the stars, but also your personal story from early days in Leiden and then across the world. Thank you so much. Really entertaining lectures. We have a couple of questions coming in. And one of the questions actually that fascinated me from the beginning, where you were talking also about the water accumulating on these dust grains. I was wondering, what are the dust grains themselves made of? Is this silicon oxide or is this something else, something richer?
Yeah, it's silicates definitely, and that's you can silicon. So you can think of SiO3 and SiO4 compounds with some fraction of iron and magnesium. We have seen pure phosphorite in space, so Mg2SiO4, even in crystalline form. So that's one of the minerals. But that would be crystalline, but most of the interstellar dust grains are amorphous, and then it's a mix of magnesium iron rich silicates, SiO3 or SiO4. Also carbonaceous material is there, and there we don't know exactly yet what kind of sort of tar-like material it is, or graphite-like material. But it's certainly some form of refractory material, a carbonaceous material is there as well.
Thank you. Another question that came in was that a question is, how soon do you think we will be able to definitely say we can detect life on other planets? I'm not sure that you can possibly answer that question, but I ask you to give it a try.
Yeah. Well, it's a very good question, and there are bets around. There are some people, they say that JWST in the coming decades will do that already. I'm always more on the cautious side. I say probably in the next 50 years. We may be able to answer that question. I think that the important part is that we are the first generation of humans that actually has the technology available to answer this question scientifically. So, of course, the question has been with us for ages, but now we really have the powerful telescopes like the ELT, the JWST, and future successors actually of JWST that are already being planned. They won't be launched until 2040 at the earliest, maybe 2050. But those telescopes will really be designed to have the sensitivity and the sharpness in order to answer this question. It could also be negative, of course, that they look at a number of stars and don't find any signal. But it's also the question, and you will probably have that later in your series, as to what is a good biomarker.
Yes.
Definitely much more than just water, more than just oxygen. You need a whole combination of chemical compounds to be saying yes.
Well, that brings me exactly to the next question, of course, because the other biomarker that was recently in the news was phosphene on Venus, where the team essentially ruled out most possible origins of phosphene or abiotic origins, and therefore at least didn't rule out a biotic origin of phosphene. Anything that you could say about that?
Yeah, well, it's an interesting case. It's so it's I think sort of the approach that they took, that they went through, is that if the detected signal is real, then the implications were that there was so much phosphine that it was very hard to produce it by abiotic ways. I think there are two two issues with that particular detection. The first one is, did they really detect phosphine? That's still under debate. Certainly one of my colleagues in Leiden has looked carefully at the data.
I thought so, yes. I saw his paper.
Is not yet convinced, and there are people that are not yet convinced.
Because essentially, if you would do the correction on the data, then if you smoothen the background in a different way, then the signal disappears, isn't it?
Yeah, it's not a smoothing of the background, but it's how you subtract the background. Yes, yeah. How do you do the calibration also of the background? So that is the first thing. And then indeed, and this is of course the interesting part of an interdisciplinary study, like the Venus team was a very interdisciplinary team, but even there's so many aspects. Do you understand, all the aspects of clouds, of the surface, what that does, the interaction between the surface and the clouds, etc., etc. So I think it's the last word has not yet been said there.
Yeah. I think also to whoever asked the question, I think if you consider that the atmosphere of Venus is essentially liquid hydrogen, so sulfuric acid. If you think about water in sulfuric acid, is not free. All the water is essentially bound, and so in such an environment, life would be pretty much impossible if you consider.
Yeah, I mean, of course, on Earth we've seen that life is quite robust. It can survive under quite extreme environments that we hadn't thought before. So I think that is the interesting part.
That's true, but even in honey, already water is so much bound to the sugar molecules around it that it is almost at the limit at which life can actually persist. Yeah, that's certainly true. Actually, the Venus story is interesting in another way, of course, as to how a planet that is about the same size as Earth, that probably initially had, when it was formed, about the same amount of water as Earth, and then completely differently developed. And of course, the lesson also for Earth that it actually developed this runaway greenhouse effect. So this is always something that you can point to, and you can learn from what happened to the climate on other planets to see what we have to be careful for with our own Earth. This is also maybe a good start to a question that Guus Boerens is asking, and he asks us, is it possible for planets to develop around a star in different planes? So you have shown the early star with a disk around it. Do all the planets have to start in that particular disk, or could you be somewhere else?
Yeah, that's an interesting question. So one of basically the densities, if you're not in the disk is of course not flat. It's a two-dimensional or three-dimensional structure. But most of basically everything forms in the midplane of the disk, where the densities are higher and where all the dust grains will actually grow and settle to that midplane. Then outside of that, it's very difficult to form a planet. What you can certainly do is you can capture a planet a rogue planet, so to say, that was formed elsewhere. The other thing that can happen is that when the cloud collapses, so in the early stages, when you're still in the very young stage, the cloud collapses and forms the disk, then actually the disk can become gravitationally unstable. And so you basically collapse a part of your disk directly into a planet. So that's a so-called gravitational instability mode that happens sort of in the collapsing cloud envelope disk interface, so to say.
Thank you. And then I have a question from Oliver Maguire, who wonders whether the water on the surface of the grains plays an important role in sticking the grains together. I think you mentioned that very briefly at some point.
Yeah. So it is here why water ice accelerates coagulation. That's because early experiments on dust grains, water ice coated dust grains, had suggested that actually that you actually stick them together more easily if they are water ice coated. More recent experiments seem to contradict that, so it's a little bit up in the air whether it really helps or not. What it certainly does is once you have ice-coated grains, it enhances the mass of solids. And once you enhance the mass of solids, then you simply grow quicker. So in that sense, the statement here is still true. Water ice accelerates coagulation, but it's not necessarily that it becomes stickier, so to say.
Thank you. I had a question myself on the molecules that you study in interstellar space, where, well, your tools are extremely advanced in terms of the detection that you need, but it's still not comparable to the tools that we have in a standard laboratory. And so you were mentioning glycine or caffeine. Can you, in such a case, go beyond the actual just connectivity of the atoms, but also maybe to the chirality of molecules that are found in space? So the question is, if you would have a potentially chiral molecule, could you see which chirality of the molecule is present?
Yeah, so there is one chiral molecule detected, ethylene oxide, but it is based on our spectroscopy. So basically, we will of course need to do remote sensing. We have incredible sensitivity. We can see molecules down to a level of 10⁻12. So we have 12 orders or 13 orders of magnitude dynamic range. So that is fantastic. But we cannot distinguish based on spectroscopy whether it's left or right-handed, at least not with unpolarized light. So if the cloud would be in the neighborhood of, say, a neutron star, which has very highly polarized lights, to trigger it, that would be perhaps a way.
Has that been achieved so far?
No. There have been ideas about that, but we haven't found a good region.
Well, any students that are watching, this is one of the questions that maybe you can go after or think about.
Yeah.
I have one final science question from Erika Georgi, and she asked whether it is why is it water that forms on the surface of the dust grains and not another substance?
Oh, yeah, good question. Well, it's much more than, it's definitely much more than just water. But it happens to be that oxygen is the third most abundant element after hydrogen and helium. So there's simply a lot of oxygen there. And hydrogen is, of course, the most important one. So that is why you definitely make water, and you make the bulk of the ice is water. But we also have other ices. Carbon will be turned into methane, nitrogen will be turned into ammonia. Carbon monoxide, in fact, you can stick 4 hydrogens on it, and then you actually make methanol. So that is many of these molecules we can actually make in the ices on the grains, and that's what we're actually simulating here in these experiments.
So just also from my understanding, so many of the molecules you showed on that slide, and I'm sure there are many more, they are not formed somewhere in space. They are all formed on the surface of these little dust particles.
Well, some of them are formed also through gas phase reactions. Water, I mean, in hot regions, you can actually make a lot of water just by gas, by the reaction of oxygen plus H2. But that requires at least a few hundred Kelvin. So room temperature, so to say. Then you can produce water in the gas phase. At the very low temperatures, just 10, 20 Kelvin, that is when you can. Then it's very difficult to make water on the surfaces of. In the gas phase. Then you really have to make it on the surfaces of the grains. And there are some other molecules that you can make very readily in the gas phase. Carbon monoxide is an example of that. Some of these long carbon chains that are seen in space, so HC7N, for example, those are also made primarily in the gas phase. But these more saturated molecules, those are the ones that primarily on the grains.
I've one final scientific question from a person called Nent Mitch Bond, who says, how probable is non-carbon-based life? But I think I'm going to defer that question until we have Lee Cronin on the show, who has all kinds of, I'm sure, strong opinions on how probable that would be.
I can give the astronomical. I can give the astronomical answer.
That would be great.
And then the point is just that carbon is after oxygen one of the most abundant elements. If you would go to silicon, you're losing a factor of 10 in abundance. So it's a very versatile element. So there's just simply a lot of it.
Very good.
And we see it everywhere. We see it everywhere in space. So.
Very good. Thank you. Then a person called Rock Bottom, and I hope that the person is doing all right, would like to know whether you had any extracurricular activities during your studies, and if so, did they help you in unexpected ways in your future career?
Well, here I was playing the violin. We were having lots of gigs at parties, playing Hungarian and Romanian folk music. So that helped me certainly in getting over my stage fright.
Okay.
I'm not sure. I wasn't active in student fraternities, for example. I was not active in that. I was active in music. And I was active in maybe other ways, but not so much in fraternities. I think the most important thing that I said here is make sure you get noticed in one way or another. It doesn't matter, you can be good in one particular topic, but you can also be good at something extracurricular or something technical. You can be a very good programmer. If you get noticed, that is the most important thing. And then people say, "Oh, that's the person to go to if you want to get that done." That's the important part.
I think that's very good advice. I think also if I look at your CV, then there is a whole page on all kinds of boards and committees and science policy functions that you have been on. So. To the student involved, you could say, well, there are many times later in your career where there's plenty of time to do lots of other extracurricular activities, if you consider them at least extracurricular.
In my case, they were, of course, quite integral part of getting things done. I mean, it was clear that for the next step in our science, we needed to have something like Alma. So it was. I put quite a bit of time, during that part of my career into making, one of many people making Alma happen. But it was very important to do that.
Which I guess,
if you're just the users of a facility rather than also the drivers. And making sure that it happens, then it's not going to be the array that you want.
Which I guess also, especially in astronomy, you don't get the chance to build many of these telescopes.
No.
There's only one in your lifetime, so it has to be the right
exactly.
one.
Yeah, it's 30 years planning, and then it will last for 50 years. So yes, there's only one. There's only one there. So you have to get it right.
Yes. Will ask the question whether there are many parallels between music and astronomy.
Well, the music of the spheres is a very good point too. But sometimes the stars are singing, actually, if you listen to them, the frequencies of their vibrations, good vibrations. But I think you will find quite a number of musicians among the astronomers and the physicists. More than I found under my chemistry friends. So that is actually also interesting.
Perhaps a question to close off the evening. But the question is, who do you regard as the most inspirational scientist of today?
Oh, I find that a very hard question.
There could be more than one, of course.
It's. I mean, I've had the fortune to work with so many inspiring scientists, and like this year's Nobel Prize winners, for example. They are very driven, but also my own mentor, Alex Dalgarno, who was basically the pioneer of astrochemistry, or I would say the grandfather, so to say, of astrochemistry. He didn't say much, but whenever he said something, it was so good. And he was sort of an example for me also to follow in the way he did science and the way he was able to connect molecules. Chemistry is astronomy.
Well, Ewine, with that, I would like to thank you again for a wonderful journey across the stars, across the universe, and also of your own life, and giving us some really, really good advice to all the students that are watching, which is essentially that you have to find something that you're really good at it and make sure you get noticed. I think that is a very...
And also I should say be passionate about it.
Well, you have to enjoy it as well, of course.
You have to enjoy it, enjoy
that's
life, enjoy work, be passionate about it, yes.
Very good too. So Ewine, thank you for being so kind to join us today and for kicking off this first episode. You really have set the standard very high, and I'm sure the others will follow later on. So I thank the audience for joining us in this live stream today and for the good questions that they asked, and I hope to see you back in 1 month. And with that, I would like to close off today, but not before thanking the organizing the committee for having the idea to set up this late night conference and for making making everything possible, and it went very smooth. So thank you all, and be safe, and see you back next month. Thank you all. Bye bye.